It takes water to make cities grow. And without water, cities would die. New York, Chicago, and Los Angeles need billions of gallons a day, from rivers and reservoirs to the water tap. A vast hidden network of tunnels, pipes, and pumps. Some are cutting edge, and some are a century old. Now, city water on Modern Marvels. October 2003. A 108-year-old New York City water main carrying more than 1 million gallons an hour suddenly burst, and swirling whitewater rapids surged through an area of several square blocks. The disruption, dislocation, and damage were dramatic. The incident pointed out how fragile and yet indispensable city water systems are. Most of us take them for granted until there's a problem. When most Americans turn on a faucet, they expect clean, pure water to flow out. They also expect their city to have plenty of water for industries, for fighting fires, and for cleaning streets. Public water supply systems in the United States provide all those things for 99% of the population. Over 250 million people.
Water supply is empowering. There are so many things that can happen when you have a water supply, and so many things that don't happen when you don't have a water supply.
On average, Americans use about 100 gallons of water per person every day. And public waterworks in the U.S. supply about 40 billion gallons daily.
It truly is an invisible empire. There are thousands of miles of these aqueducts and tunnels all underneath the city, crisscrossing and moving. There's very little space down there. They've built so much. And these guys have really built, like the men who built the skyscrapers up, they've built the skyscrapers down.
Some of the technology used in today's city water systems has been around for millennia. Sanskrit writings from 4,000 years ago talk about the importance of purifying drinking water and describe various methods, including boiling over a fire and filtering through sand or charcoal. 2,700 years ago, qanats, sloping tunnels carrying groundwater, were being used in northwestern Persia.
The qanats are basically horizontal wells that are used for irrigation. These are developed originally in the area, mainly what's today Iran. They spread throughout the area into areas like Spain, into parts of China.
Around 312 BC, 4 centuries after qanats first appeared in Persia, construction on the renowned aqueduct system of ancient Rome began. An extraordinary feat of engineering. They brought water to the city from as far as 57 miles away. Over a period of 500 years, 11 aqueducts were built to bring water to Rome, and some sections are still functioning today. Ancient Mayans in the Yucatan Peninsula got their fresh water from naturally formed underground sinkholes called cenotes, to which they attached great religious significance. The Maya considered the cenotes portals to the underworld, where they would journey in the afterlife to meet gods and ancestors.
Probably the most well-known one is the cenote at the big site of Chichen Itza in Yucatan State. And this has yielded a tremendous amount of materials, offerings that were tossed in over the years. Fancy pottery, and very late in the history, gold, and a few humans, for good measure.
In larger Mayan settlements south of the area where cenotes are found, huge reservoirs were constructed to capture runoff water.
At Tikal, which is one of the larger Maya sites in the southern lowlands, probably held about at least 50,000 people in that city. They had, just in the central precinct of Tikal alone, the reservoirs could hold something in the area of about 200,000 cubic meters of water, quite a bit.
Residents of medieval London might have been envious of the Mayan reservoirs. At the beginning of the 13th century, the increase in London's population was creating a growing pollution problem in the existing water supplies, which came from local wells and the Thames River.
Across all of London there were then these cesspits, and there were, of course, these wells, sometimes right next to each other, in ways that, were just extraordinary.
In 1236, construction was authorized on the Great Conduit, which would bring drinking water to the city from a spring at Tyburn, 3 miles away. Eventually, several conduit houses were built in London. The stone buildings were not only used for storing and dispensing water, they also served as social centers.
This was a place where people gathered during festival times. They decorated the side with garlands, they painted slogans on it, and on real special occasions, like, for example, the coronation of Anne Boleyn in 1532, they stopped the flow of water and put wine in so that everybody could have wine delivered to them.
Still, many Londoners continued to get their drinking water from the Thames River, despite the pollution from human and animal waste dumped in the river. The resulting illnesses weren't associated with the pollution because of lack of knowledge of the microorganisms that cause disease.
Sometimes the night air was blamed for certain types of death that would come. Every summer it was almost regular, however, that the so-called sweating sickness would come in, which is probably a type of typhoid that we know now, but they didn't know it.
Like the residents of medieval London, early New Yorkers were completely unaware that their drinking water was making them sick. And thousands would die of waterborne diseases, like cholera, before they made the connection. The attempt to bring fresh water to New York City would lead to some of the great water projects of the 20th century. Manhattan's fresh water initially came from shallow private wells, until the first public well was dug in 1677, in front of the old fort at Bowling Green. By the late 1770s, Manhattan's 22,000 residents were getting most of their drinking water from the highly polluted collect pond in the heart of the city.
Because people were bathing in the collect, it quickly became dirty. It became incredibly fetid. There was a dead body which occasionally washed up in it from a crime scene. People would find dead animals, feces.
The contaminated water led to a disastrous cholera epidemic in 1832.
It went from hundreds and then into the thousands of people who died from that epidemic. Kids would plead for water, and then the water that they would give them was the very thing that was making them sick and only made the epidemic worse.
The situation deteriorated even further in 1835 when a small fire broke out in a single building on Wall Street. It was a cold winter night. Wells were frozen over, and so were the rivers.
And within 24 hours, all of Lower Manhattan was ablaze and in ruins. Millions of dollars equivalent were lost from business and industry. One of the worst disasters in the history of the United States. And it was these events, these really cataclysmic events, that finally set New York on a concerted program to say, we need to solve this crisis. How can we do it?
In 1837, construction began on the Croton Aqueduct, which still carries water to New York City today, providing about 10% of the city's water supply. The 30-mile-long brick pipeline, extending from the Croton Reservoir along the east bank of the Hudson River to downtown New York City, took 5 years to complete, with up to 4,000 laborers on the job at one time. In 1842, when the aqueduct finally went into service, President Tyler and former presidents John Quincy Adams and Martin Van Buren came to the Big Apple for the opening ceremony and watched water gush for the first time from the Croton Fountain near City Hall.
People recounted in elaborate fashion their first bath, their first shower. Things hard to imagine what it was like to be able to go into your house, turn on a tap, and have water.
The Croton Aqueduct was considered an architectural marvel. Most of it was an 8-by-7-foot arched tube of brick and stone, buried 15 to 30 feet beneath the ground. But there were elevated sections like the High Bridge, an arched brick overpass that took the aqueduct across the Harlem River to Manhattan. It became a popular tourist attraction in the late 1800s, with sightseers traveling 8 miles from the city to stroll across the 1,400-foot-long span.
Then, as always happens, because of the supply of water, because of the nature of New York City, the city quickly expanded, and already within 12 years, there was an editorial in the New York Times saying, we need more water, we need more water.
When you think of the immigration that was occurring in the end of the 1800s, New York was just exploding, and that Croton network just wasn't able to meet water supply demands.
And this time, they looked even further afield, and this time, their plan and vision was even bolder. And what they did is they decided to build an aqueduct all the way out to the Catskill Mountains.
The new aqueduct from the Catskill Mountains would be 92 miles long, 3 times as long as the Croton Aqueduct. It would run down alongside the Hudson River and at one point cross the river.
This is another hand-built aqueduct. This was the working man. Down there was sticks of dynamite and steam locomotives and mules hauling all that rock out.
With the Croton Aqueduct, they decided to cross the river in the aqueduct above the river. With the Catskill Aqueduct, they decided to go beneath it. And for over a year, they would sit on these boats pitched in the river, often in storms and rain, trying to do soundings, trying to literally lower things down to figure out where the bottom of the river was so they could decide how far they had to dig down on the banks to get underneath it. And there was at one point people and engineers raised their hands in frustration and they said, this river's bottomless.
But eventually the city's engineers did find the bottom of the river and made the daunting discovery that they would have to tunnel at a depth of 1,200 feet to get to the solid and stable bedrock beneath the river. It was a task that seemed impossible, but they would have to find a way. What they didn't know is that the system they were building had an Achilles heel, a potentially fatal flaw that has New York City engineers worried today. Only 1% of the fresh water consumed daily in New York City is used for drinking water. City Water will return on Modern Marvels. When New York City water engineers set out in 1907 to build a new aqueduct from the Catskill Mountains, one of the most difficult challenges was digging a tunnel deeper than they had ever dug before. In order to cross underneath the Hudson River, they would have to tunnel at a depth of 1,200 feet.
1,200 feet is nearly as deep underground as the Empire State Building is high. So it gives you some sense of scale of how enormous the engineering was to do this. And so what they did is they started to dig from both banks, literally from the sides, and they began to dig like an inverted triangle coming down like this until the two sides literally met 1,200 feet beneath the river at kind of almost like a pincer.
After crossing under the Hudson River, the new aqueduct would flow into City Tunnel Number 1, a huge new tunnel that would run the length of Manhattan, 900 feet deep. Work on the 18-mile-long Tunnel Number 1 began in 1911 and went on for 6 years. When completed, it would be the longest tunnel of its kind in the world, capable of carrying 500 million gallons of water per day. The workers of Tunnel 1 were members of a proud profession that continues to build the New York City water system today. Known as sandhogs, they've been laboring underground, unknown to most New Yorkers, for decades. They got the name from their work in the sandy bottom of the East River, laying foundations for the Brooklyn Bridge.
Starting at the absolute bottom of the economic ladder, the hardest, toughest, in a sense, most dangerous job out there that you could find. Fathers passed on those job opportunities to their children, and a culture grew out of that.
Construction of the 11 to 15-foot diameter tunnel was particularly dangerous where it crossed the East River to carry water to Brooklyn. Natural groundwater made the ground so soft that the shafts in which workers descended to the tunnel became watery death traps.
Every time they would dig, the soil would cave in on top of them. So what they decided they needed to do was to sink something called a caisson.
Pneumatic caissons filled with pressurized air had been used earlier in the building of the Brooklyn Bridge. These concrete and steel structures weighed about 2,000 tons each. They were sealed on all sides except the bottom, and as they were lowered into the soft ground, compressed air was pumped in, pushing out the mud and water.
That pumping of the air created a real safety health hazard because it created an environment where the workers would get the bends, so they were only allowed to be down there for, 2 hours.
The bends, also known as caisson disease, can happen when pressure on the body is removed too quickly, causing the formation of nitrogen bubbles in the blood and tissues. Sometimes the intense air pressure would cause a dangerous blowout in the walls of the caisson.
It was basically a high, shrill, kettle-like screeching, which would echo in the caisson. And basically it meant there was a rupture in the lining of the caisson wall, that the air was now escaping, created an incredible suction, and everything in the tunnel was going to be sucked towards a small opening. And because of the pressure, the opening could widen very quickly, and everyone would drop their picks and run
Most of the concrete-lined tunnel number 1 had to be blasted through solid rock. During the first 3 years of construction, 10,000 pounds of dynamite were used daily. By the end of 1912, a total of 2.5 million pounds of dynamite had been used, and 14 workers had died in blasting accidents. The tunnel was finally finished in 1917, and a lavish opening ceremony was planned at a fountain in Central Park. Entitled The Good Gift of Water, the pageant had to be canceled because of rain. Tunnel number 1 was an engineering triumph, but for a city growing as fast as New York, it would be inadequate within a few years. Over the next decade, population expanded eastward from the Bronx and Manhattan, and by 1929, water consumption was 35 million gallons a day higher. Construction began on tunnel number 2 to supply Brooklyn and Queens. The tunnel would be fed by a new aqueduct from the Catskill region.
It connects with City Tunnel number 2, which, together with City Tunnel 1, delivers all of New York's water to 8 million people in New York City. Obviously, they are of crucial importance. Without one or the other, half the city would be without water.
In the 1950s, New York City water engineers made a disturbing discovery when they tried to shut down a section of City Tunnel number 1 to inspect it.
They had built valves in the bottom of shafts, and these valves, they would literally turn them. They would turn, they almost look like a steering wheel on a submarine, sticking out of a hatch. So in 1954, the city goes down, the engineers go down, they start to turn the handle. And as they start to turn the handle, it begins to tremble, begins to shake. There's too much pressure on it. It's too old. The valve's corroded. They can't shut it off. They couldn't repair it. They couldn't even find out if it was about to burst or about to break. It scared the bejesus, as one engineer told me at the time, out of everybody.
If you lose this system, something that New Yorkers take for granted day in and day out, you'd have a very different New York City without water. And that is, one, a daunting challenge, and one that makes the third water tunnel so critical.
City Tunnel number 1 has been in continuous use without a shutdown for inspection or maintenance for well over 100 years. Hundreds of sandhogs are now fighting a crucial battle to complete a new tunnel as quickly as possible.
There's no way to bring water to Lower Manhattan or from 59th Street down without tunnel number 1. Once we finish constructing the third water tunnel, we'll be able to turn off the first water tunnel, get in there, look at what its engineering challenges are for something that it's 100 years old. People forget everything breaks at some point. A 100-year water tunnel at some point starts to fail, and you're now seeing the kind of snap, crackle, and pop within that system.
Some of the sandhogs building tunnel number 3 believe the only thing preventing tunnel number 1 from collapsing is the pressure of the water pushing against its walls.
One of the engineers and contractors, he told me, probably more starkly than anyone else, that what nobody knows is that we're facing a potential apocalypse. Those were his direct words. And so once again, an enormous project began, and it began in 1970. It became, for those who understood it, a race against the clock.
No one understands that race better than the sandhogs of today, who are building City Tunnel number 3, many of whom come from a long line of tunnel workers.
My uncle, my cousin, they all sandhogs, and then you join with them. And I've been in a sandhog for 27 years. When I go down there the first time, it was exciting. I said, wow.
Sandhog Scotty Chessman has a PhD in geology. After working as a geologist for the city, he decided to go back to the job he loved best.
When you get down there, it's the root core of the Appalachian Mountains, anywhere from 1 billion years ago to 400 million years ago. If you're going through here and you see a beautiful cross-section of what it was like, the physical activity that took place, the deformation, the heat and pressure, and the imprint on the rock. And it changes as you go along. You know, it's almost a PhD thesis every 100 feet.
The 60-mile-long tunnel number 3 will extend from Yonkers through the Bronx, down to the southern tip of Manhattan, and then over to Brooklyn and Queens. Longer, wider, and with more sophisticated control systems than its two predecessors, its construction ground to a halt for nearly a decade after New York City went bankrupt in 1974. And it's not scheduled for completion until 2020. It's being carved out by a gigantic machine, similar to the one that dug the Channel Tunnel from Britain to France, called a TBM, or tunnel boring machine.
It has a large head, 13 foot roughly in diameter, and it has a bunch of cutters on it, and they press up against the face at 1.5 million pounds of thrust, which comes out to roughly 65,000 psi per cutter. This tunnel boring machine has these large grippers. It locks it out on the wall. It has these large hydraulic cylinders that push the head forward, and the head rotates and presses on the face and creates these chips.
As the TBM moves forward, it's up to the sandhogs to clear out the chipped rock it creates, which is called muck.
Now this is the actual muck. This is the last conveyor of the system, you see. And it's muck. You can see some chips in it, but it's pretty finely ground. So the muck you're seeing right there probably came from the heading 8,000 feet ahead of us probably 20 minutes ago.
Whenever the sandhogs prepare to descend to their workplace deep beneath the city, they're aware of the dangers involved, and that awareness keeps them alive.
5 guys that I've worked with have been killed on the job and then here. A lot of guys have been maimed, and it's sad that it happens, and I don't want it to happen to me, and they didn't want it to happen to them, but sometimes things happen. You know, safety's a big issue. You know, everybody wants to go home.
There's always one last thing to do before getting on the elevator for the 600-foot trip down.
This is a check-in, check-out board. It's it's an OSHA requirement. If there's ever an accident down there, we'd like to know how many people are down there if you have to rescue anybody. So it's a requirement that you flip over your tag. So as I'm going in, I'll flip over my tag for red, and that indicates that I'm in the tunnel.
24 sandhogs have died in the construction of Tunnel Number 3. Some believe they may have given their lives to prevent a catastrophe.
If one of those systems collapsed over the next 20 years, it would be a disaster of mega proportions that would overshadow all the disasters combined. It would truly be a calamity. The stakes are as high as they've ever been. They're as high as they were in the 1830s. People just don't realize it because the water is still flowing.
While we're building the third water tunnel, we definitely and unequivocally do not expect catastrophic failure in the near term. But if you don't do it now and you don't start building it now, it's definitely not going to be a place where that risk is really facing the city.
The city of Chicago has never had to look far for its water supply since it's situated on one of the Great Lakes. But it did have to build the largest purification plant in the world to keep its drinking water clean. New York City residents consume an average of 1.1 billion gallons of water a day. That's about 300 million gallons less than in 1988, when the city launched a major conservation campaign. City water will return on Modern Marvels. Chicago, the husky, brawling city of broad shoulders, as poet Carl Sandburg once called it, is a city built on water, by water. Today, the Chicago water system includes more than 4,000 miles of water mains, ranging in size from 4 inches to 60 inches, which supply water to 5 million people. But in 1835, this city was home to a grand total of just 350. The population quickly grew to 60,000 in 15 years, and this placed a heavy burden on the city's water supply, which came from a water intake at the end of a 150-foot-long pier on Lake Michigan. It was pumped into a wooden reservoir and then flowed by gravity through wooden pipes into town.
This is a wood water main, which we estimate to be over 100 years old. It's typical of what it was prior to 1850. This one appears to be coated with some type of tar, which would probably be typical of what they would do when they installed them.
In 1864, the city started construction on an engineering project that made headlines around the world. A tunnel that extended 2 miles out into Lake Michigan, the longest tunnel ever bored up to that time. The tunnel was dug through clay 60 feet below the lake's bottom and was lined with brick to a finished diameter of 5 feet. A pentagon-shaped wooden building called a crib, which would protect the intake shaft from ice and the elements, was built onshore, towed out into the lake, and sunk to the bottom. The term crib came from the wooden pilings which were sunk into the lake bed. 30 years later, the wooden building was replaced with a brick one, but the term crib remained, and the Carter Harrison crib is still there today. The Chicago Water Department tug, which is also an icebreaker, makes regular trips to maintain it. Modern Marvels went aboard with Richard Rice, the head of the Chicago Water Department, for a trip to the Harrison Crib, which looks much as it did when it was built over 100 years ago.
Plaster walls, wood trim. We have living quarters for about 19 individuals who may be out here at any given time during the year to do work.
In the early days, there was always somebody at home at the crib.
We actually had a crib tender. That was actually a title in our budget, a crib tender who lived here 24 hours a day. Rumor has it that they had the best meals in town cooked out here.
The shore end of the tunnel was connected to a new pumping station that opened in 1869. It had the capacity to pump 18 million gallons a day, which was 60% more than the city needed at the time. The Chicago Avenue pumping station is still an essential part of the downtown water system, with a total of 6 working pumps that can produce 200 million gallons a day.
The original pumps were steam-driven. We've converted and modernized the station. These are one of our older electric pumps. This pump that we see here will be pumping 30 million gallons per day.
The Chicago Avenue pumping station, which now includes a restaurant and a theater, and the historic water tower across the street, have become major tourist attractions in downtown Chicago. For a while, the 2-mile-long water tunnel under Lake Michigan provided an abundant supply of clean, fresh water for Chicago. But as the city grew, tanneries, glue factories, and other new industries belched effluent directly into the Chicago River, which was already polluted with sewage. By 1890, Chicago sewage was flowing all the way from the Chicago River to the intake crib 2 miles offshore. Chicago was hit by outbreaks of dysentery and typhoid. To keep pollution out of the lake, the city broke ground in 1892 on the largest earth-moving project of its time, the 28-mile-long Sanitary and Ship Canal, which was larger than the Suez Canal in Egypt. The canal reversed the flow of the Chicago River, making it the first river in history to flow away from its mouth. 8,500 laborers used mule-drawn plows, steam shovels, and dynamite to move nearly 30 million cubic yards of earth. Reversing the river's flow led to a dramatic reduction of pollution in Lake Michigan, and by 1908, Chicago's typhoid rate had dropped 91%. Chicago eventually built more intakes and cribs to bring water from Lake Michigan. They include the still functioning Deaver Crib, located beside the old Harrison Crib, and connected to it by a steel walkway.
In 1935, the Deaver Crib was completed, and that was actually a 16-foot concrete-lined pipe that actually is beneath the floor of Lake Michigan at a depth of about 150 feet.
The Harrison Crib, taken out of service in 1998, still serves as the living quarters for maintenance crews working on the Deaver Crib. As Chicago's population grew, a large purification plant became necessary. The Jardine Purification Plant, designed to filter and treat more than 1 million gallons of water per minute, was completed in 1964. It's the largest water treatment plant in the world. Huge pumps bring lake water from the Deaver Crib into the plant, where it goes through a vast system of sand and gravel filters to remove impurities, called particulate.
Each one of these filters is a conventional rapid sand filter. It's basically a couple feet of gravel topped by a couple feet of sand, and the water travels through the sand and is filtered. It will trap most of the particulate on the top.
Aluminum sulfate is added to cause particulate to coagulate into larger particles called floc. This happens in flocculation basins, where a large paddle wheel stirs the mixture.
Each one of these flocculation basins has 4 passes where we slow stir the water to form the floc before it starts its journey through the settling process.
Several other chemicals are added to the water before it leaves the Jardine plant. They include chlorine for disinfection, fluoride to fight tooth decay, and blended phosphates to prevent corrosion in water mains and pipes. In the plant's testing laboratory, technicians perform numerous tests to monitor the quality of the water 24 hours a day, 365 days a year. Millions of samples are taken at the plant every year to ensure that the water meets the standards of the Safe Drinking Water Act. The incoming raw water is also monitored for unpleasant tastes or odors.
With the odor monitors, we basically use the human nose. In raw water, you may smell an earthy smell, you may smell a fishy smell, you may smell a moldy smell, you may smell chemical or a phenol smell.
If the water fails the sniff test, the Jardine plant will add powdered activated carbon, which can remove tastes or odors. Tiny carbon particles are extremely absorbent, like sponges.
After the water has completed the treatment process, it flows by gravity through our outlet tunnels to our 12 pumping stations located throughout the city.
Chicago's location on Lake Michigan means it has a huge supply of fresh water on its doorstep. Los Angeles has no such luck. So finding the water necessary to turn this patch of semi-arid land into America's second largest city has never been easy. The Chicago Avenue Pumping Station and Water Tower were the only public buildings to survive in the area destroyed by the Chicago Fire of 1871. City water will return on modern marvels. Diamond Valley Lake Reservoir, about 80 miles east of Los Angeles. It was the largest earthworks construction project in U.S. history and one of the boldest ideas for water storage ever conceived.
The Metropolitan Water District and the engineers there looked at what was essentially a ring of mountains and said, what if we connected them? And so they created a bowl that is elevated to the mountaintops. It's an extraordinary idea.
Unlike most dams, a river does not run through it. Water for the huge reservoir comes by pipeline from the state water system in California's Central Valley and from the Colorado River. The Diamond Valley Lake Reservoir has doubled the water storage capacity in Southern California. Construction began in 1995, and the reservoir was completed 5 years later. $100 million worth of earth-moving equipment, including some of the largest dump trucks in the world, was used to carve out nearly 150 million cubic yards of soil and rock.
When you put that on a scale of those kind of projects that have been done worldwide, that's 7th largest in the world in terms of moving that amount of material, but we did it quite fast. And we were moving enormous volumes of earth and rock every day, 20 hours a day, 6 days a week for 4 years to do that.
Once the dams were completed, the next step was to fill the reservoir with water. With a capacity of over 250 billion gallons, it took more than 2 years to fill it up. The Diamond Valley Lake project includes a large pumping station to get the water into the reservoir.
The pumps actually draw off that smaller lake or that pumping pool and push water through the mountain that we're standing on to an outlet tower, which allows the water to be delivered into the lake.
The pumping station contains some of the largest variable speed electric motors that have ever been built. The variable speeds allow them to adjust to changing water levels in the reservoir. Motors can also function as generators when the flow of water through the pumps is reversed.
Each of the 12 motors is a Westinghouse 6,000 horsepower motor. They were built in Texas, and they were transported here and then placed on top of the Mitsubishi pumps. They're capable of pumping 175 cubic feet per second. Now, the unique thing about these particular units is they're also capable of running in a generator mode, in which case we can produce 3.3 megawatts of electricity when they're in gen mode.
The Diamond Valley Lake project is a visionary investment in the future. As with projects launched by California water planners decades ago, it's expected to pay huge dividends. If ever there was a city built by water, it's Los Angeles.
We've always used water in California as a means of removing the natural limits. Clearly, God never intended large numbers of people to live in the Los Angeles basin. It's a semi-arid plain. And yet we had the accidental truth about the development of California is that everyone came west initially for the gold rush and then turned left, going south to the area where the water was not.
The story of the early growth of the LA water system is largely the story of one man, William Mulholland, the first director of the city's water department. He was an immigrant from Ireland who first worked as a ditch tender for the city.
It's very rough, uneducated, not trained as an engineer, but it's supremely confident.
By the age of 31, Mulholland was head of the Los Angeles Water Department. and searching desperately for new sources of water for the city's growing population. That water would come from the Owens River, more than 200 miles to the north. Construction on the 223-mile-long Los Angeles Aqueduct began in 1908 after a newspaper campaign to get Los Angeles residents to support the idea of a public bond issue to pay for it.
Simultaneously, the city fathers announced the existence of a drought that no one had noticed before. But in order to float the bonds that were necessary to secure voter approval, it wasn't enough simply to say that there was an abundant supply available for future needs. What followed then was a largely fraudulent, as it turns out, campaign, but only the first of many by which the fear of an impending drought was used to create popular support for new waterworks.
With the financing in place, construction finally began on 34 miles of open unlined channel, 39 miles of concrete channel, and 98 miles of covered concrete conduit. Some of the conduit was big enough to drive a car through. 6 million pounds of blasting powder were used to build the aqueduct. When it finally went into service in 1913, bottles of Owens River water were handed out to the 30,000 celebrants who traveled by car, wagon, and buggy to the opening ceremony at the San Fernando Reservoir, north of the city center. Although residents of Los Angeles welcomed the new water supply, farmers in the Owens Valley weren't too happy about having millions of gallons of their water siphoned off daily. In 1923, both the city and the Owens Valley area were experiencing water shortages. Confrontations escalated, and there were incidents of sabotage. During the 1920s, there were 10 attempts to blow up the aqueduct with dynamite. The construction supervisor at Diamond Valley Lake, Dennis Majors, recalls his grandfather's stories of patrolling the aqueduct on horseback with a rifle to prevent sabotage.
They had to get out there every day early in the morning, starting at 5 o'clock, and head 25 miles in one direction, patrolling that thing. They did tell me, well, they never had to arrest anybody, but they probably got close from time to time. He carried an old 1870 Winchester 25-35 with a scabbard on his horse, and maybe that's had some effect on not having to arrest anyone.
The Los Angeles Department of Water and Power that Mulholland helped create went on to become the largest municipal utility in the country. But Mulholland's career ended unhappily with his resignation in 1928 after the collapse of the St. Francis Dam near Los Angeles. Mulholland had supervised the dam's construction and inspected it just hours before it burst, killing 450 people. Because of the city's huge population growth, Los Angeles now relies on a complex system that delivers water not only from the Owens Valley, but also from the Sacramento and San Joaquin rivers via the California Aqueduct, and the Colorado River via the Colorado River Aqueduct. The water sources are coordinated by the Metropolitan Water District of Southern California. Formed by Los Angeles and surrounding municipalities in 1928, the MWD now encompasses an area from Ventura in the north to San Diego in the south.
Not just Los Angeles, but its child, the Metropolitan Water District, have always built way ahead of demand, have more water than they are likely ever to need, and have been able to survive the droughts that have struck California in the last 20 years in far better condition than many other parts of the state.
One huge untapped source of drinking water for California is the Pacific Ocean. Desalination plants can change seawater into fresh water, but the only plant doing it on a large scale is 3,000 miles away from Los Angeles. The Metropolitan Water District of Southern California provides residents with up to 800 billion gallons of water every year. City water will return on Modern Marvels. Water desalination plant is the only operating seawater plant of its kind in the country. The plant serves about 2.5 million Florida residents in Tampa, St. Petersburg, and the surrounding area, providing 10% of the fresh water supply, or about 25 million gallons a day. To change seawater into drinking water, the plant uses a process known as reverse osmosis, or RO.
This is raw seawater. This is the water before it goes into the first stage of the filtration system. the sand filters. The sand filters are the next stage of filtration before the water gets into the RO process.
The water is pumped through filters to remove impurities before entering the reverse osmosis system.
These are 5-micron cartridge filters that are made of like a yarn substance. These filters are able to capture any suspended solids that may make their way through the sand filters. We don't want any particles, any suspended particles, passing on beyond this point in the process, because that could result in fouling of the reverse osmosis membranes.
In regular osmosis, when two water volumes are separated by a semi-permeable membrane, water will flow from the side of lowest concentration of soluble matter, like pure water, to the side of highest concentration of soluble matter, like salt water. In reverse osmosis, pressure is exerted on the side with a concentrated solution, the seawater, to force water molecules across the membrane to the freshwater side, in effect, filtering out the salt.
Following the cartridge filtration step, the saltwater pressure is then boosted with this 2,000 horsepower high-pressure pump. That pump pressurizes the water up to 1,000 pounds per square inch. That's enough pressure then to pass on to the membranes, which is really the heart of the reverse osmosis process.
Each one of the blue pressure vessels contains 8 of these reverse osmosis tubes.
This is a cross-section of a reverse osmosis membrane. The way this works, the salt water under the high pressure, 1,000 pounds per square inch, is passed into the membrane. That high pressure forces the fresh water through the membrane, leaving behind a salty, concentrated solution.
In the entire plant, there are 10,000 reverse osmosis membranes.
If you unrolled all these membranes and just put the membrane surface area back to back, it would stretch for 223 miles.
The concentrated seawater left over from the desalination process is diluted and released back into the ocean. The desalination project at Tampa Bay is being studied closely by other water departments across the U.S., including the Metropolitan Water District of Southern California.
The question will be when we go there, not whether we go there, in my opinion. A seawater desalination program in Southern California could be a very important complement to the other water resources, so that when we have droughts, or if we had an earthquake that knocked out one of our pipelines from the Colorado River or the State Water Project, you have a palette of resources that you can draw upon, and seawater desalination would be a nice complement to that.
As fresh, pure water becomes an increasingly valuable resource, some experts are calling it the new oil, and predicting that wars may someday be fought over it. Ideas that would have been considered bizarre a few years ago are looking increasingly viable. A Greek company, Aquarius Water Transportation, has been supplying fresh water to several Greek islands using huge floating plastic bags. The bags, which are towed to the destination by tugboat, can each hold nearly 8 million gallons of water. Another company has proposed wrapping entire icebergs in plastic and towing them to locations that need water. 70% of the Earth's fresh water is locked up in the polar ice caps from which icebergs are formed.
People have been talking about icebergs for a long time. It's sort of a captivating idea, and there are certainly areas of the world that have limited options, and just towing down an iceberg to areas of the Middle East or even some islands in the South Pacific that are limited in their water supplies could be very attractive.
Futuristic techniques like these may be practical in isolated applications, but for the most part, public water supplies seem destined for the foreseeable future to continue using tried and true methods, some of which date back thousands of years. It's hard to beat rivers, reservoirs, pipes, and pumps, but unless today's water planners have the vision, foresight, and public support that their predecessors had decades ago, the consequences could be dire.
Tonight on Heavy Metal Friday, she broke the back of the Luftwaffe, reduced Berlin to rubble, and turned the tide of war.
I don't think we could have won it without the B-17.
The B-17 Flying Fortress, tonight at 8 on the History Channel.